Hello everyone. Thank you for being here. We'll start our session now. We have Nils Nolde here, who will be presenting about Valhalla, place of lowest severity. Nils is joining us from Berlin, and I'll leave the floor to Nils. So it's yours, Nils.
Thank you very much. Thank you very much all for coming. So I'm going to present Valhalla today. I'm going to start with the cliche. So who used Valhalla before? Okay. Who tried to use it and was utterly confused on how to? Okay, good. Just one is good. Okay, so Valhalla, I think everyone sort of has heard about it before, but also there hasn't been a public presentation in an international conference for like 7 years now. So I thought I will try to, make up for that. So just a few words about us. So we're a small software consultancy based in Berlin. Obviously, we're mostly dealing with routing and routing-related projects. We started out with very broad geospatial software development, but then doubled down on routing. I became a Valhalla maintainer. And we are also, I think one of our more core benefits is that we can also make arbitrary data sets routable with OSM ingesting routing engines, which are all the open source ones. We do also like to work with other routing engines such as OSRM, PG routing, and we do also like to do QGIS plugins. We have a couple, not very well maintained at the moment. There is one coming up that we're working on since 2 years, but it's a bit of a, yeah, I will announce when it's that far. So Valhalla is, wait a second, yeah, now. So in 2014, a brief history of it, in 2014, MapZen developers had the idea for Valhalla. Actually, MapZen was scooping up a whole routing team from MapQuest, and those guys were having the idea for the architecture of Valhalla. And then in 2015, it was actually published on GitHub and to the public. And then in 2018, for 3 years, there was a lot of feature development going on. In 2018, MapZen had to close. Mapbox got lucky enough to get the Valhalla engineers that MapZen got from MapQuest before. And then in 2019, MapZen, and including Valhalla, became part of the Linux Foundation, which I'm to this day not quite so sure what that really means. And in 2020, we came in. And would I have known back then how much effort it would be to work myself into C++ and Valhalla and routing? I'm not sure if I would have sacrificed it all. It was really a rough 1.5 years. But I made it, and now I actually made it to a maintainer. So there's a few, the most well-known Valhalla users probably is Tesla, who uses it in their in-car navigation engine. And Mapbox is almost 100% relying on Valhalla these days. Yeah, but both are not contributing back very much lately. Tesla never, Mapbox not since 2 years. Valhalla profile, just give a broad outline. So it's in C++ 17. Obviously, it consumes OpenStreetMap data. It has an interesting architecture that kind of offsets it from the other routing engines that are out there. So there's a hierarchical and a tiled routing graph. So that means it's kind of akin to map vector tiles. And it also has a very highly flexible request parameterization. So that means a user who wants to request a route can influence the route finding in many, many ways. But I'm going to show you more of that later. So just to talk a bit about the high-level features, I find Valhalla, like objectively, not only because I like it a lot, objectively Valhalla is the most feature-rich routing engine, I think, at the time right now. That's open source. So we, of course, have all the routing APIs, like normal A to B routing. isochrones, matrix, map matching. We have a couple of other APIs, like for elevation, we can ingest elevation. And you can query for the altitude at a certain location or for the entire line. We have a very excellent navigation engine. So that is for instructions, when should a user turn, at what point in the route. And it's like, yeah, it's like the narration, right? What the real-time navigation does for you. And in total, it's translated into almost 30 languages, almost to 100%. That's also the main reason why Tesla and Mapbox chose Valhalla as a routing engine. And then we have time-dependent routing. So that's not entirely unique, but it is very well implemented in Valhalla. So apart from all the access restrictions that we have in OSM in theory, which are not very well populated, but we could consider all the access restrictions, the time-based ones, but it also naturally leads to something like public transport. That was a Google Summer of Code project last year, where we could ingest raw GTFS data into Valhalla directly. That's finished and it's better working. Then also it leads to traffic consideration, of course. So we can consider historical and real-time traffic information, which is not open data usually. And we have Python bindings, which makes it very easy to use the C++ library directly from Python instead of going via HTTP route. And we also, that was one of the core principles, I think, when Valhalla was designed, is that it is usable on mobile phones. So since it's a C++ project, we can compile Valhalla for iOS and Android, and it can also be used offline. And finally, I think it's worth noting that we don't only have a JSON API, but we also have a protobuf API, so that helps a little bit with lower bandwidth usage. And there is a potential for gRPC, but that's not really implemented yet. So what is probably most interesting for someone who wants to run Valhalla themselves is a bit about the requirements that a server needs to have. If you want to, there's two different scenarios, right? So one is you want to build a graph, and one is you want to serve the graph and actually answer requests. So you build a graph once in a while, like every week or two, and you can do it on a server that has around 60 gigabyte RAM for the entire planet. It will take like 36 hours approximately on 16 threads. That's what I know from the OpenStreetMap service. And it requires around 300 gigabyte SSD disk. Like the faster the disk, the better, obviously. And then the service, if you want to run it as a service, so once you have built the tiles and you're going to transfer the tiles to another server, that doesn't need to be as big. You can actually run it, like it has a minimum requirement of like 50 megabyte approximately, which makes it ideal for offline scenario. And well, it's still pretty performant. It's not OSRM performant, but it takes like a few milliseconds for shortest routes and like a second from Madrid to Moscow, which is like 2,000 kilometers, probably more. So the Valhalla graph, there's two things you should remember about maybe in the end, is one, it's tiled, and the other one is it has hierarchies. So it's a bit like map tiles. So it's akin to zoom levels, I would say. We have 3 hierarchies, which are based on the highway OSM tags. And so we have a level 0. This is the biggest tile size. It has a 4-degree tile size. And there, all the motorway trunk and primary highway roads. And then we have the level 1 tile, has a 1-degree tile size, and it has all the secondary and tertiary tiles. And you can see the extent of it in the, over Germany. So this is like 80 tiles, I think, or 70. And then we have level 2 and 3. So level 2 is still used for normal road routing. Then we have all the low-level unclassified, residential, everything that, that is very common, like the most common highway text. And on level 3, it's like an addition that was done after the initial graph structure was there. Level 3 has all the transit nodes. All the transit nodes and transit edges. So the thing in like the Valhalla graph, it's tile based, right? And each tile is represented by one file on your computer. And we organize it in such a way that one tile, one graph tile, has all the edges that start in that graph tile. And we have like abundant properties and attributes for every edge. And that is what makes Valhalla also very flexible. So since it's one file on the computer, each of these tiles. And for example, if you see the level 0 tile up there, it has an ID of 3286. And that just means it's because we index our graph in a way that we start at -80, -180, -90 degrees, and then we just go row-based. So it's like 0, ID 0, ID 1, ID 2, and so on. And then we go up to like 180 degrees, and then we jump one row up. Yeah. And so this is like the, yeah, you can basically, you can calculate the lat long from the tile ID, since it's predictable. So we have a 4-degree tile size. You know it's the 3286 tile ID. So you know it's actually its lower left corner is at 54 degrees north, 4 degrees east. And the hierarchies, so the hierarchies are, right, the level 0, 1, and 2 tiles. And they are connected via special nodes. We call them transition nodes. And that actually makes also, like we have a very unperformant routing algorithm. It's just an A-star in the end. But these hierarchies and the ability that we can transition between them is what makes this fairly performant. So on the next one, I'm going to show you a small video which shows how Valhalla will load the tiles. So we're going to start here and there, and it's in this case it's a unidirectional, so we're going to be linearly following this path, and we're going to have an intermediate location around here. So in the beginning, what happens is that we're going to start at the on level 2 tiles. So that might be some residential road. Someone wants to route from home to his friend. And we're going to load the very small level 2 tiles that have a lot of edges in them. But then as long as the route progresses and the routing algorithm progresses, we're going to very soon switch to the level 1 tiles, which have less edges in them. So it's easier, like it's not as much RAM intense to load them. And they also have the edges and the roads that are progressing faster, right? Because they have a higher hierarchy. So then it wants to jump as quickly as it can from level 2 to level 1 tile, and eventually landing on the on the level 0 tiles. And that is where all the motorways are located. And then, since there's an intermediate location, it will have to do the reverse process again. So we'll go from level 0 down to level 1, and eventually to level 2 tiles, where we'll find the intermediate location. And then going towards the end, it has to again do the other thing. Go from level 2 to level 1 to level 0, and eventually getting to the destination. And what time is it? How much do I have left? Oh. All right. So, tiles and hierarchies. Actually, does give quite a lot of nice properties that we can use to make it easier and nicer to work with Valhalla in the graph. So you can cut regional extracts. Since we know that tile IDs refer in the end to locations, to lat longs, we can actually use that property to just take a complete Valhalla graph and just cut regional extracts. So we just package a bunch of tile files, and that will represent a graph that Valhalla can route with. Then it's also very resource friendly. Like that was one of the core principles that was responsible for the architecture of it. Valhalla only loads tiles into RAM which it needs to find a route. And since it's using memory mapping, it's a system that will decide what to cache and what to uncache. And we can actually build a Valhalla graph in parallel. So that decreases build time quite a lot. So you could do it in theory, very little people do it. Then it's also, we still, even though we use just a A-star and Dijkstra, we're still quite performant. And that's because of the hierarchies and the shortcuts that we do. And well, in the future, we want to have some some improvements on the graph itself. So incremental updates would be nice to have. So we can only rebuild tiles which actually had OSM changes. And MVT endpoint would be also nice because then you can use Valhalla to build vector tiles for rendering. And yeah, so the next thing, the graph is one thing, but we can use that graph, that richly attributed graph, to do some actual routing. And one of the other core things that Valhalla is really good at is flexible costing. So costing is really what will eventually find the route. Every edge has, like, it really boils down. It really boils down to an edge has a time and a cost. And time is what is really important to use to users, right? Like that's contributing to the ETA. And the cost is what the routing algorithm will really look at to decide which path will be part of the final route. So we have many attributes stored on the graph for each edge. And one of them is, for example, maximum weight. We also inflate it with elevation raster tile files to get the maximum and minimum slope. We do also extract the administrative features to get the attribute of is an edge crossing a border. And we even do a density calculation to determine whether we're in probably rural or rather urban environment. And we have like 3 different parameter categories. One is like fixed costs, which does impact both cost and time. So this is added to the final ETA, but it's also influencing the routing algorithm itself. For example, a toll station, you would add 10 minutes, and then the routing algorithm would say, okay, this is more expensive, I'm probably rather avoiding it. But you also would add 10 minutes to the final ETA. Then there's a penalty. That is only like a fixed time that is added to the cost. For example, you want to avoid service roads with 20 minutes. That tells the routing algorithm, like, don't go over service roads. But if you do have to, then don't add it to the final ETA. Then the factor. So factors are multiplying cost. It's usually between 0 and 1. A factor of 0 will often avoid things, and a factor of 1 will often favor things. For example, you can, again, avoid toll roads by setting use tolls of 0.0. If you set a use toll of 1.0, you will actually favor toll roads. We have a bunch of profiles. We call them costing models. They're like the fixed sort of the fixed parameters that you cannot influence. So for example, a pedestrian cannot go on a motorway, right, or on a freeway. But then we have all these costing options that you can send per request, and that will actually influence how the route will look like in the end. So you have a maneuver penalty, for example, which is like an additional cost to do a turn or a maneuver. You can favor or avoid slopes. You can do an actual shortest route by distance, instead of, which will ignore all other costing options. You can pass time information for departure and arrival, which, if you have traffic, will obviously take that into account. You can, for a bike-only costing model, you can avoid bad surfaces, such as cobblestones. You can tell for pedestrian route to rather prefer lit roads. So inside a tunnel, for example, you don't necessarily want to walk through a dark tunnel. Many, many more. There's a full list in the API reference. So just to show a few of it's just a showcasing. So this is like the execute polygons. If we place a polygon right where it actually would like to route, with all other parameters being the same, it will just avoid it and go another route. Then we have something called top speed. So that is, the default is 140 kilometers. It's basically saying how fast do you maximum want to go with your vehicle. And if you put it, for example, to 60, then the route will change from not taking a highway, because we're also, we're also, like we will penalize roads that have a maximum speed limit of higher than 60 kilometers, if you set that option. So we'll prefer non-highways. Max weight, 10 tons is obvious. We're gonna avoid everything that's not liking anything above that. For example, this little bridge in Berlin. Then we have something called expansion. I think in Esri terms, it's called network view. It's mostly producing pretty pictures, but it can also be very relevant for data analysis. Very recently, multimodal again, which is based on GTFS, and this is really not looking that good. But it's pedestrian and transit, right? So in this case, you only see the direct connections because there wasn't any shapes attached to the GTFS. And yeah, it's quite obvious what it does. But we're very happy that it's enabled again. Then there's traffic. I'm just going to show this because it's pretty. And so this is like the heartbeat of Berlin, where depending on the time of the day, the isochrones, you will have a further reachability, while in the morning and the afternoon and the rush hour, the reachability is quite low. And I really like this visualization. So we got some possible improvements. Our graph building is not as good as it could be. We have a single-threaded OSM parsing stage in the beginning of the graph build, which takes 12 hours currently, and it's almost impossible to speed up right now. But we want to multi-process or multi-thread that eventually. Then there's incremental graph builds. I already talked about it, which could be very interesting for humanitarian use cases. There is MBT generation. I already talked about that as well. And we want to improve the GTFS ingestion, which currently just takes an awful lot of time, and it's not going to be fit for a global instance yet, just because it would take weeks to generate. Of course, if anyone wants to fund, I'm here. We have a couple of related resources and projects. I did find in the very beginning, it's a daunting experience to start with Valhalla. So our company, or me specifically, focused on making it a bit more accessible. We actually, FOSS4G, the German German, how you say, foundation, is sponsoring the cost for it, but we are maintaining and running the server for the public Valhalla instance. We have the web app which is open source. We have a Docker image. We have a QGIS plugin. We have the packaged Python bindings. And there's also some demos. And that's it. Thank you very much.